course, when we're classifying linear higher order differential equations, they also may end up being non-homogeneous. Today, we're going to talk about what we can do with non-homogeneous linear higher order differential equations. When we refer to a non-homogeneous linear higher order differential equation, we're talking about a differential equation that still has some function of x times the nth derivative of y with respect to x, and so on down until we have some function of x times the derivative of y plus some function of x times y. All of that setup remains the same from our homogeneous differential equation. That's the setup of a linear higher order differential equation, regardless of whether it's homogeneous or non-homogeneous. What changes is for a non-homogeneous equation, it's going to be equal to some function of x. So that means somewhere in the differential equation, maybe before we've put it into this form, there are terms that involve x's or constants that aren't multiplied by y or any derivative of y. Now, it's important that that function of x, it may be 0 every once in a while, but it's not identically 0. So it is not the 0 function. Now, to talk about non-homogeneous equations, we actually lean on homogeneous equations quite a bit, because non-homogeneous equations have the potential to get very complicated very quickly. So we're going to first talk about what is a particular solution. Well, any function y sub p free of arbitrary parameters that satisfies a non-homogeneous linear nth order differential equation is said to be a particular solution of the equation. This is no different than it was for first-order differential equations. When we had a particular solution, it had no arbitrary parameters in it, and it satisfied the differential equation. Now, keeping in mind that we can have a particular solution to our non-homogeneous equation, we're going to define an associated homogeneous equation. That is, if we have y1, y2, and yk all are solutions of a homogeneous linear nth order differential equation, namely the one shown there, on some interval I, and then we have our particular solution yp, that's a particular solution of the non-homogeneous linear nth order differential equation that's shown there, then on I, the linear combination y equals c1 times y1 of x plus c2 times y2 of x, adding all of those up to ck yk of x, plus our particular solution yp of x, is also a solution of the non-homogeneous equation. Therefore, that original homogeneous equation that we were working with that gave us our solutions y1 to yk is called the associated homogeneous differential equation. And this gives us our first theorem for the day. The theorem is for a general solution to a non-homogeneous equation. So we're going to let yp be any particular solution of a non-homogeneous linear nth order differential equation on an interval I. And we're going to let y1 up to yn be a fundamental set of solutions of the associated homogeneous differential equation on I. Then the general solution of the equation on the interval is given by y equals c1 y1 of x plus c2 y2 of x plus all the way up to cn yn of x plus yp of x, where ci are arbitrary constants for all the values of I. Now you might notice that that solution, that general solution of the non-homogeneous equation, looks a lot like the solution of the homogeneous equation plus that one particular solution that we had. So this is where the idea of a complementary function comes in. So the general solution of the associated homogeneous differential equation is called the complementary function for the non-homogeneous differential equation. And in fact, we can get the solution for the non-homogeneous differential equation by simply adding our particular solution onto that general solution for our associated homogeneous differential equation. It's also worth noting the superposition principle for non-homogeneous equations. Now, non-homogeneous equations, the function of x that we're dealing with may be rather complicated. And so the superposition principle is going to help us deal with that. So if we let y sub p sub 1, y sub p sub 2, all the way up to y sub p sub k, get double subscripts going on here, bk particular solutions of a non-homogeneous linear nth order differential equation on an interval I corresponding in turn to distinct functions g1, g2 up to gk. That is, supposing that y sub p sub I denotes a particular solution of the corresponding differential equation. That's our non-homogeneous differential equation with just set equal to that g sub I of x function, where I can be anything between 1 and k. It could be any of those distinct functions that we're setting it equal to. Then y sub p of x equals the sum of all of my subscripted y sub p's. So y sub p sub 1 of x plus y sub p sub 2 of x all the way up to y sub p sub k of x. That is a particular solution of the non-homogeneous equation that's given by having the basic linear setup of a differential equation on the left-hand side, and on the right-hand side I have g1 of x plus g2 of x plus gk of x. So if I have a complicated function of x on the right-hand side of my differential equation, if I can break it into its component parts by splitting it into some g sub 1, g sub 2, g sub k, then I can use the superposition principle to find a solution for the larger non-homogeneous differential equation.